Hi guys, I'm Matt, and I'm the little guy in the corner of your screen here. And I'd like to tell you about this machine learning project that I've been working on, and I hope you find it interesting. So, what you're seeing is a little video game, and you're the player, the guy at the bottom of the screen, and you're shooting. And these aliens, the the other guys, are shooting at you, and on you can see a score in red. It may be a little hard to see, but right now that score is 300. That's a pretty good score. If you get hit, your score goes to zero. And what I've done here is I've trained the agent or the player to play this game and to try to get a really high score. And right now it plays about the same as a human. It plays similar. It gets a similar score to what a good human would get. So that's good. So you may be looking at this and saying, well, this game looks like a 5-year-old wrote it and or a 10-year-old. And I think a 10-year-old could do a pretty good job of programming the agent to get a high score. So why is Matt excited about this? And you're kind of right, but over the next few minutes, let me tell you the details of this. And I hope you'll see that there's actually a lot of really advanced technology behind this. And in a way, this is cutting edge work that, um, well, whether it's exactly cutting edge or not, I leave it to you to decide. But it's it's pretty advanced, and it's uh, shows the incredible capability of machine learning. So with that, let's let's go through this. Okay, so let me just introduce the story a little here. Um, right now, I'm showing you a web page. Uh, this web page is from a company called Unity, and they make what's called a game engine. So what this allows you to do is program from very simple to very advanced video games. And what I'm showing you here is obviously a really simple video game. So it's called a game engine, and the reason it's called that is that instead of having to rewrite the whole world every time you want to write a video game, you can use this Unity tool, and makes it really easy to include physics in your video game and score and all of that. So what I've done here is I've written this simple game in Unity. Okay, let's keep going. If you want to learn Unity, this is a good course you could take. It's from a company called Udemy, and this guy is named Ben Tristram, and he will teach you how to program in Unity. And in fact, the little simple game that I showed you, I took this course, and that course they show you how to develop a game, this game. So that's why I'm showing you this. Um, okay, so so once you have your game in Unity, now we wanted to make it suitable for machine learning. Unity isn't natively designed to do machine learning, but Unity came out. The nice people at Unity put this package on GitHub, and this is essentially Python code. And basically, Unity will communicate with this Python uh, engine running on your machine. So as the game develops, Unity engine will constantly send the data to this code, which is also running on your machine, and then this will understand the data and it will train the agent, and then it will send back to Unity. It'll actually control the agent. So what you're seeing is that the game sort of runs in Unity. It sends data to this code called ML agents, and then ML agents will send instructions back to the machine what to do. So that's sort of how this works. And again, this is all free, which is super cool. Okay, let me keep going here then. My code, by the way, I've also put it on GitHub, and I'll have a link to it, and it's all free. So again, if you want to repeat what I've done, just go to this page and download it, and you can do that. So I hope people will enjoy doing that. Uh, the code that I showed you, ML agents, essentially relies on machine learning, and a very widely used machine learning is called TensorFlow. This is a framework for machine learning. So if you want to write a machine, a deep learning machine, you can do that in TensorFlow. And what I'm showing you here is TensorBoard, and this is a way to sort of monitor your progress. So what I'm showing you here is as the system learns, first it was getting a very low score, but as it learned, the score got better and better. You can see it actually takes a couple of days to train this agent, which is kind of interesting. I mean, it seems like a simple game, but I actually had the computer running all day and all night for a couple of days to train it. So it's a slow process. And you can imagine actually that if this took 3 days to train, like sometimes you didn't get the result you wanted, so you had to try again. So actually, I've been playing at this for a couple months. So it's really quite insane. If you want to do reinforcement learning, uh, you have to have some time to do it. That's true. Also, I don't have a very powerful computer, and maybe if I'd used a more powerful computer, it would have been faster. Another interesting thing about this curve is that it's not smooth. You can see it's kind of bumpy, and when you learn something, sometimes you'll unlearn it. That is, if you're throwing a baseball, sometimes you'll get better at it, but sometimes to get better, you have to get worse. You have to try something that doesn't quite work, but then you refine that and then it gets better. So you can see learning isn't really a smooth process, it's a bumpy process. Also, the game, like maybe at this particular point in time, the game was really easy. It gave you a really easy scenario, and maybe here it gave you a hard scenario. So, anyways, you can see the score that you get is not continuous, it's bumpy. Let's go back to the game because it's fun watching. I can honestly sit here and just watch it. It's kind of addictive. Uh, you know, it's kind of like watching your cat or something. Okay, so let's see. So I talked about Unity. I talked about uh, Udemy, ML agents, and TensorFlow. Let me just talk a little bit more about this game in particular. I mentioned before that this game comes from largely from a course that I took, but I did make some important modifications. You can see it's black and white and not very beautiful. The reason that is that I wanted to feed black and white data to my machine learning model because I thought if you send it color, that's more data you got to send. So I wanted to make it the least data that you had to send to the program. Uh, Also, I added what you can see here is that there can only be a few aliens at a time and only a few bullets. So I didn't want to make the game too hard. Also, the player can only fire 2 bullets at a time. And the reason I did that is I didn't want to make the game too easy. So that makes it a little more challenging. And um, also, you can see every once in a while, there's a alien that comes down right above the player. And the reason I added that alien was because I didn't want the player to just stand still and just keep firing. So by adding an alien above the player and giving him a shot at the player, this makes the game a little harder. It's kind of interesting that the solution that it found, if you watch this for a few minutes, you'll see the player just sort of moves back and forth in the same zone when it sees, well, sometimes it makes mistakes even though. If I trained it for a couple of days, maybe it'll do better. But one doesn't have all the time in the world. But anyways, you see it just kind of wiggles back and forth in the same range. And when it sees a bullet coming, it sort of moves to the right and stays there for a while. or maybe it moves back to the left. It just sort of toggles, and that's sort of interesting because it's really not at all like I play it as a human. Like when I play it, I sort of move all over the map and stuff, but this just has that very precise movement back and forth, which seems to work pretty well. Um, maybe it annoys me a little bit. Like if it did annoy me, maybe I could put in another aspect of the game that would prevent it from playing in this way. But actually, it doesn't annoy me that much. I'm kind of okay with it. Uh, you can see the game is running pretty slow. I think this might be my computer. It's not the fastest computer in the world, and it's training, or it's not training right now, but I don't know. It could run a lot faster, and uh, the agent would still do pretty well. Sometimes it does. It kind of speeds up for no reason sometimes. Let me talk to you a little about Unity, the game that I wrote. I already mentioned that it's a programming language. So this language, um, this window is the sort of the game window, and it's how you program Unity. And you develop something called a scene, and you can put all sorts of objects in the machine in the scene, like a player and enemies. Uh, so I mentioned before, it's really very sophisticated. This is a pretty simple game, but it's still actually pretty complex to program. Uh, it's a very powerful language. You can see it's natively C sharp, and here I'll show you some code. Let's see if I can show you that. Uh, this is actually the code of Unity. So basically behind all of these sort of pictures, there's code that tells the system what to do. And I've written some of that. And this is all sort of object oriented. And what that means is that everything does what it should do. Like the player plays and the aliens do their thing. And there's sort of a program for every aspect. So if you're familiar with programming, I think one type of programming is called procedural, where you say, okay, player do this, alien do this, player do this, alien do this. But that's not how this works. You have one program that represents the player and one program that represents the agent. And this is really good for gaming because you don't necessarily always have to think about this happens and this happens. And in some sense, everything happens at once. So that gamers like object-oriented programming. Um, another thing you can see here, well, it's not that easy to see, but this piece of code that I'm showing you here is for something called the agent. I mentioned before the agent is the guy that played the games, and what is happening here is the agent is sort of receiving all the data from the aliens and the player, and then it sends all that data out to ML agents that control software. So this is sort of the hub that gathers all the data, and then the hub that receives the data from ML agents. So there's sort of a communication process between Unity and ML agents, and this is at the heart of the process. So this is something that wasn't really in the original program, and I've added it a bit. So you can see there's a fair bit of work to do in the coding, but it's not that difficult. It's a little tricky to be honest. I did spend a while to get it right. Okay, let's switch you back to this game here. What next? Now I want to tell you about reinforcement learning a little bit, which is super interesting. And so let's talk about that. So how does this thing actually learn? I'm glad you asked. So reinforcement learning at its core is like training a dog. You know, when the dog does a good job, give it a cookie. When it doesn't do a good job, no cookie. I hope you never hit your dog, but just don't give it a cookie. That's fine too, right? So the dog wants the cookie, and he'll try to do the thing that you want him to do. He'll try to catch the frisbee, or he'll try to, I don't know, whatever. So that's the way this is working too. Like when the player does something good, he gets a higher score, and when he gets killed, that's bad. Um, there are a lot of challenges with reinforcement learning. What the way I just described it to you, that might sound really simple, but it's actually a lot more tricky. It's a whole field of research and fascinating. So one reason why it's a whole field of research is this concept of delayed rewards. And the problem is, uh, let's say you want the dog to open the jar of peanut butter and then, or maybe that's not, but let, let's say you want the dog to open the door, and then the reward will be later when the dog can open the door, go in the house, and go in the kitchen. So it's this idea of delayed rewards. You do something good now, but you won't be immediately rewarded for it. You'll be rewarded in 10 minutes. And so it becomes really challenging to have the game understand that it did something good now. The reward was 10 minutes later. So how does it associate that good action with the delayed reward? That's a big challenge of machine learning and reinforcement learning. So, so let's talk about that a little bit. The algorithm that we're using here is called the PPO algorithm. That stands for something, but I'll look it up. Let's look that up. PPO algorithm. Proximal policy optimization. Wow. So let me just explain that a little bit. I'm not an expert in this, but here's my understanding. At the heart of this PPO algorithm is something called the actor-critic approach. So the actor is the agent, and the agent is trying to get a really high reward. But I mentioned before the concept of delayed reward. And so to estimate your reward, you can't just look at the reward in the next like millisecond. So what do? Well, what we do is we have the critic, and the critic is another network, and it's going to estimate the total reward that you're going to receive in the next few seconds. So uh, let's see. Go well. Let's say my peanut butter, my concept of opening the door wasn't a good example. Let's think of a better example. When I buy a sandwich, I give you my money, and then like maybe a minute later, you give me my sandwich. So that's the exciting part, getting the sandwich, but I have to wait a minute to get it. Okay. So the critic, his job is to estimate the future reward that you can anticipate. So what the critic is going to say is, I saw you just make this move, and it's my belief that in the next minute, you're going to get a delicious reward. So the critic, his job is to sort of look ahead and predict the anticipated reward. So the critic is a network that is going to train to estimate the valuation in the best way, the future valuation. Meanwhile, the actor is going to train based on what the critic is telling him. So the actor is going to take an action, and then the critic is going to say, okay, I saw that action, and I think it's going to be worth, 100 points, and 100 points more than the average action that you could take. So that sounds really good. So the actor is going to say, oh, that's a good action. So I'll try to do that sort of thing more in the future. Or the critic could say, that was a really dumb move. I think you're about to get killed. And the actor would say, well, I'll try not to do that in the future because the critic says it's a bad idea. So the actor is essentially being trained by the critic. Meanwhile, the critic is being trained by sort of watching what's happening. And he says, well, I told the actor that this was going to get him 100 points. Let's see if that really happens. And, maybe it gets him 200 points. And the actor says, okay, I understand that. So next time I'll tell him that it should have got him 200 points. So the actor and the critic are both simultaneously training and learning. So that's sort of the idea. And like I say, I'm not a super expert, so please feel free to correct me if I got this wrong. Okay, so that's the idea of the actor and critic. Let me talk a little bit about hyperparameters. So that's a big word, right? Uh, YAML file. Hold on for a second. Let's open our YAML file here. So I'll just talk a little while the file is opening. So when you build a neural network, you're you could run this ML agents, and then you get to set some parameters. How big is the network? What is the nature of this network? And a lot of these parameters are called hyperparameters. I don't know why it's called it. It's a cool name, but it basically means the parameters of your simulation, your model. So I'll just point out some of the parameters that I set here that are useful. Uh, this buffer size and batch size, this is determining how many steps you take and how many steps you take before training. So what this is saying is you're going to take 4,096 steps. I'm going to take all that data and then I'm going to train. So basically I'm going to play a little bit and then I'll take all that data and train. And then I'll play a little bit more and then I'll train. That's sort of the way this learning works. And then here, this learning rate describes how fast you learn. So every time it trains, that's like an update step. But you don't want to totally update because then you would get very unstable learning. So the learning rate describes how fast you will update. So that's it's not a critical parameter, but it's something. This hidden units, this is a parameter of the model. So this hidden units and this number of layers is sort of telling us how big our neural network is. So 512, that's a lot of units. So what that means actually is you have 512 units and then you have another layer and this is fully connected. So what's 500 squared? That's 250,000 weights that need to be configured, which is not a huge neural network. I don't know. It's on the large side. The larger your network gets, the longer this will take to train. So you might say, hey, I'll make a really, really big network. But I think that would be a bad idea, especially in reinforcement learning. Um, instead of taking days to train, it'll take weeks to train. So, but on the other hand, if you make your network too small, then it won't be capable of doing the calculations that you want it to do. So that's a trade-off. This gamma here, this is related to a discount factor. So before I told you about estimating future rewards, that is, you're gonna estimate, when I get the sandwich, that'll be uh, 1 minute from now, and I want to, even though it won't happen for a minute, I want to give you the sense of that reward right now because that'll help train you. That'll be used. So um, the gamma is a discount factor. That means the further something is away in time, the less value it has to you. And that sort of makes sense. Like a sandwich a minute from now sounds really good. But if you give me a sandwich 10 minutes from now, that's not that exciting. If you give me a sandwich 3 hours from now, I don't know. I'll, I just won't be motivated to take that action if the reward is so far away. Uh, part of this discount factor makes these reinforcement learning mathematically tractable. Like if you didn't have this, then you would have to estimate the reward forever, and that would be really challenging. So it sort of puts a time bound on things. In this game that I've showed you, the time scale is a few seconds. So this gamma is 0.99. There's 60 frames per second. What this means is that things that happen in a few seconds don't really matter. This time horizon is also related to how far you look. So let's see. What I think what this is saying is that the critic should tell you, should estimate a reward based on the next 100 steps. So it shouldn't try to look like 10 minutes into the future. It should only try to look 2 seconds into the future. And I think that is actually an important hyperparameter. That is, if you set your time horizon too long, then the critic is trying to estimate so far in the future, and it can't really do that. So it's good to set a reasonable time horizon. Over here, there's something called use curiosity. I think what this does is it uh, like how much you sort of try to explore. Uh, that is, sometimes you'll find a good solution, but there might be a better solution, and you might be in a local minimum. So this can sort of jump you out of that local minimum, but you don't want it too strong, or you'll be too jumpy. So these are all parameters. This comes with this ML agent, so you can see I'm a little unclear on it, and I didn't write ML agents. I'm just a user of that. So, but I have some sense of what they're doing here. So these are the hyperparameters that I've set, and hopefully the hyperparameters aren't that critical. Like if you set gamma equal to 0.98 rather than 0.99, hopefully the game would still work. But I think this time horizon was important. And another another thing that I'd like to discuss here. Let's see. Let's go back to this game because I think it's fun just to watch it. Okay. Um, so originally when I wrote this game, I said, well, you have like the player and you have the bullets and you have the enemies, and I'm going to make a list of all of these. So the player is at coordinate, 10 comma 10, and the alien is at coordinate 0 comma 0, and there's up to 5 aliens and up to 6 bullets, and I'm going to make a list, and it turns out maybe 50 data points. I could specify the position of every thing that you needed to know. So I just sent these 50 coordinates to the program, and I thought it would be able to train. And it really failed here. When I just sent the list of coordinates, it really couldn't figure out at all what was going on. Or if it did, it did a crappy job. So I spent a while just watching this stupid player get hit by bullets, and it wouldn't avoid the bullet because it didn't understand what a bullet was or where it was. So that was really frustrating for me. So eventually I switched. Instead of sending it data, I send it an image. So the image is essentially what you see here on the screen. Actually, it doesn't include the background and it's lower resolution. It's only 100 by 100. But basically, I send the program a lower resolution image, and the image is larger. So if it's 100 by 100, that's 10,000 data points that I'm sending. So I'm sending it a lot more data. So to me, that seems like it would prefer the first way where I just send it this short list, but actually it preferred getting the image. And once I sent the image, it really did a lot better. So I found that a little surprising, but I guess it has to do with the nature of machine learning. And my sort of hypothesis is that when you send it the data, the image, it can kind of understand the spatial relationships in a way that wasn't obvious when I just send it the list. So on the other hand, there's a theorem that says neural network should be able to figure out anything like that out. So I, I really was a little puzzled, and I really didn't find any good references online to explain it. But I think the lesson might be if something looks like an image, it's probably best idea to give the neural network that image rather than give it a list. Okay, well, I think that's kind of all that I had to say. We talked about how I wrote the game, how you might write a game like this, the nature of reinforcement learning, certain architectural choices that I made. And, in the beginning, I said, well, this game looks kind of silly, but there's actually a lot behind it. And I hope you can see that. And maybe in my next game, I'll do something more complex and exciting. But, I'm kind of excited about this as a simple start. Uh, I'll put a lot of links to this in the video, all the web pages that I've shown you, and my GitHub so you can replicate this work. And thanks for watching. I hope you enjoyed it. It was a really fun project for me. And bye bye.